Heyo. So let's talk about what happens when we do electrophilic aromatic substitution when we have directing effects on a ring. So if we've already got a group that's already on the ring, that's going to influence where all the other things go, right? So we got to figure out where it's going to go. And then we also have to think about like what happens in the case that maybe we have multiple groups on there and they're competing for the location that a new group goes onto. So just to kind of reiterate what we've already talked about, the blue, these spots that are right adjacent to where this mystery group is right here, this would be the ortho position. I'm going to label that with an italicized O with a dash. The pink spots, those are like 2 bonds away from the group that's already there. This is the meta position. So I'm going to do an italicized M with a hyphen. And then the last one in the orange that's right here on the very end across from it, that's going to be our para position, which is an italicized P. So we have to think about all these things. So let's just get started. First of all, this chart is really helpful and really important. So we have 4 categories of things that we got to think about. We have activators and deactivators. And then what if they're ortho-para directors? Because generally something that's going to direct ortho is also going to direct para. And we'll see that in a mechanism probably later on. And then meta directors. So let's just start off with that. So what's a good activator that's also an ortho-para director? So we have, this is not a comprehensive list. These are just some examples. So that would be something that's like an alcohol group, or maybe even some kind of ether, so OR or something like that. We could also have something that's an amine. Now that could be, this is a primary amine. We could have a secondary amine, or even a tertiary amine. So we have 2 R groups coming off of there. Now I will say that the things that are OH or NH2, those are going to be more activated than maybe the things that have the carbon groups on there. Activators that are also ortho-para directors, that could be really just any carbon group. So an alkyl group of just kind of any sort. And so you can look in your book for a more comprehensive list, but this is kind of the idea that we've got going on right now. Ortho-para directors that are deactivators. So there's actually one category. So generally activators are ortho-para directors. Deactivators, meta directors. There's one category of deactivators that are also ortho-para directors, and those are halogens. So anything that is F, Cl, Br, or I. Any halogen. Really, that's it. Now what about activators that are meta directors? So interestingly enough, this category does not exist. There is no activator, at least that we know of, that is a meta director, and I don't think that there ever will be for a pretty decent reason. That the activator is something that is electron donating. So I'm going to write that down. The activators are electron donating groups, and deactivators are electron withdrawing groups. Looks like an N, but it's a W. Electron withdrawing groups. And so because activators are electron donating groups, I don't think that there's ever going to be a meta director, because anything that's going to donate electron density is going to end up directing ortho-para. The reason that these guys, even though they're electron withdrawing groups, are ortho-para directors is because they can, oddly enough, donate via resonance. I'm going to put donate in quotations there. So they can donate using resonance. Okay, what about the last list? What are some things that are deactivators and meta directors? So there's actually a couple. These are any things that are generally withdrawing groups. So that's going to be, let's just say, some kind of ketone or aldehyde. I'm going to put R there, put a little star there. that star, I was just going to say, could be a C or an H. So either one is fine. We could have some kind of sulfonate group. A nitro is good. And then this is another strange one. What about like an ammonium or aminium ion? This one's really interesting. So this one would actually be an electron withdrawing group. Unlike its other amine counterparts, this one has no lone pair electrons that it can donate into resonance. This one's plus charged. So if you'll notice kind of a difference between these, let's just do this in gray. All of these that are partial, or that are connected to maybe wherever our ring is going to be, these are partial plus or fully plus. Because you know how the oxygen, the shape of the nitro, I'll just draw that nitro group out. The shape of this nitro group looks like this, right? And so you can see how this is fully plus there. This partial plus, and that's fully plus. So all of these things here are either partially positive or fully positive. They're withdrawing electron density away from that ring. And that's part of the reason why they're meta-directors. Okay, so let's talk about this real quick. So I want to talk about directing effects, and I want to increase the difficulty as we go along these different problems. So as any good person would do, I'm ranking the difficulty level by Taco Bell hot sauce packets, because I think that that's a pretty good analogy. So let's just give that a try. I'm just going to circle my group, and then we'll decide where it should go. So this is my only group on here, so he doesn't really have any competition. This is a meta-director, so let's revisit. It's a deactivating meta-director. And so what positions are meta to that? Well, there's this right here, and there's this right here. Now, the question that I have for you is, like, is there a difference between those two spots? No. Absolutely not. This is a symmetrical molecule, so it doesn't actually matter where we add our Br2. So I'm just going to draw that final product on one of those spots, knowing that both are identical. We add bromine. That's a bromination. Awesome. Okay, what about this next one? Let's change up that color. Let's do purpile. Okay. That is a toluene molecule with a methyl group right there. That methyl group is kind of weakly activating, but it's still activating nonetheless. It's an ortho-para director, so we've got to think about all the possible spots that we could add something. We could add there or there. Those are both of the ortho positions, or alternatively, we could add there. Now, you might not have seen this before. This is really interesting. So this is an example of an anhydride. And so anhydrides are super reactive, and they're going to react with aluminum trichloride to make an electrophile that's going to do the same thing as any kind of Friedel-Crafts acylation. So I'm going to say Friedel-Crafts acylation. Awesome. Awesome, awesome. Okay, so we have all three of these spots to add, and I also have the workup step, the aqueous acid workup step afterwards. I think the best place to add this group is going to be the para position, so I'm going to star that. I think this is the best position, and the reason for that is because of steric hindrance, right? It's nice to add across the molecule if possible, or farther away, because there is a little bit of steric hindrance coming from that methyl right there. Okay, these are pretty simple so far. Last one, what about this last one? I'll just go back to red. This is a nitration, and so let's look at the groups that we've got on here already. Okay, so this is an ortho-para director just like this. These are our groups. And so I'm going to say this one wants to direct here, here, and here. And this one wants to direct, turns out, there, there, and there. Pretty simple. Let's just say that it's going to add there though as its major, because that's going to be farthest away from the biggest group, right? So we could think about adding here versus here versus here. This is closer to a bigger group. This is close to both of those groups, and this is farthest away from the bigger group. So I'm going to say that this is our winner. Let's draw that. Okay, awesome. There we go. We just got through eating our cheesy gordita crunch with some verde and mild sauce. That was not too bad, was it? Let's try it again with the hot and the fire sauce. Kick it up a little bit. Okay, multiple groups now. We have a lot to think about. Let's think about this one. This one's a ortho-para director. It's an activator. And this guy is a deactivator. It's a meta director. And we're sulfonating. We're adding an SO3H group. So the purple, that's going to direct meta. Meta's here and where that methyl already is. Okay. So that's the only spot for that one. Now this one's ortho-para. That's unfortunate because why? Well, these are all the different groups, or different locations rather, around this ring than where this one suggests we should go. So who wins? I think that that's what we really need to consider right now, is like, who is going to win when we have this battle? So I'm going to give this claim that the strongest activator and by the same notion, I'm going to say weakest. So if I only have deactivator, I'm going to say the weakest deactivator. But in this case, I have an activator. That is what wins directing effects. So the strongest activator, or in turn the weakest deactivator, wins the directing effects. Why is that? Well, activating groups speed up the reaction. So it would make sense that the thing that is activating this ring to react is the thing that would cause the reaction to get sped up so that it would direct to the spot that's faster reacting. And the weakest deactivator rather than the strongest deactivator, that kind of makes sense because we still want to have the thing that makes the reaction go fastest direct where the group is going. And so I'm going to go ahead and say it's not this purple one. And I'm also going to say it's not here because of steric hindrance. So we kind of have to fight between these two. I'm going to say this one is probably our best bet just for the reason that it's a little bit less sterically hindered. So I'll write that out. Cool, wonderful. Okay, let's give this next one a shot. What is this? This is a really nice activator. And so I have two rings that I'm thinking about. Am I going to add to this ring or this ring? One thing you have to know is when we're dealing with pure naphthalene, it's going to add to one of the positions that are right next to the other rings. But when we have a group on there, we have to think about that. In this case, I have an activating group on this fused ring system. So I'm going to add to the ring that my activator is on. The very opposite is true for deactivators. But in this case, I have an activator and I'm going to add to the ring that the activator is on. So I could add here, which is the para position, but it's already taken up, so I don't get that luxury. So I have to choose between my two ortho positions. Now I mentioned to you already that when I have just a plain ring, I'm going to add to the ones that are right next to the fused ring. So I'm actually going to choose this one as my major location that my groups are going to get added to. I'm adding a BR. So I'm going to draw my one ring in, and then my second ring in H2, and then I'm going to add BR to that location right there. Wonderful. Okay, next one. Let's look at this. I've got an alcohol here. That's a really nice strong activator. And then I have an ether who's also a strong activator, but not as strong as my OH. So I'm just going to start off with red. He wants to go ortho-para. Here, or here, or here, but that's already taken. What about the purple? Wants to go here, or here. Wonderful. We have a dilemma. We're having problems where we have two activators and they're all saying different things. Like I said before, the strongest activator is the one that wins. In this case, OH is slightly stronger than OR. And so I'm going to choose the red and not the purple. And I'm going to choose the spot that's para. So I'm just going to say that this is my starred location. So let's draw that in. And then I've added a nitro group. Okay. Couple more examples and then we'll look at a synthesis problem. That'll be tough. Okay. Now these are all fire, no hot sauces, only fire sauce left. Okay, cool. We have a nitro group and we're adding a carbon. So let's write this. Okay, I've got this. This is a deactivator. So that deactivator would preferentially add a group meta. Now, I've tricked you a little bit by giving you this problem. And the reason that it's tricky is because this is a very strong deactivator, like incredibly strong of a deactivator. And this is about to be a Friedel-Crafts acylation. The problem with this is that Friedel-Crafts acylation does not occur on deactivated or like strongly deactivated rings. So the Friedel-Crafts acylation or alkylation is not going to occur on strongly deactivated rings like this nitrobenzene. And so I'm actually going to give this a big fat NR for no reaction. That's a surprise to us. Okay, next one, moving right along. Let's just circle our two groups. Here's one. And then here's the other. So the purple is going to direct ortho-para. The para position's already taken, so just ortho. And red is going to, of course, direct ortho as well. And of course, these are going to be in opposition to one another. So there's the challenge. I'm going to make the claim that this nitrogen is the better activator. And so I'm going to say that this or this are going to be acceptable, but this is an identical molecule, so it doesn't actually matter. So I'm going to write what that answer is going to be. I'm going to do this Friedel-Crafts acylation here. All right, so wait, what? Hold on, let me think for a second. What did I just do here? Why is it shaped like this here, but shaped like this there? Okay, so you're going to have to think about this, and we'll talk about this in recitation on Friday. But you need to figure out why this was shaped like this here and shaped like that there. Think about that in terms of mechanisms. Try that on your own. Okay, next one. This one's a tough one. So I've introduced sodium hydroxide, then water with HCl. And so actually, I want you guys to try giving this a try on your own. And I'm gonna leave this one as a blank. I'm gonna let you try this on your own. Maybe I'll put the answer to the structure name in the comments or something like that, but I want you guys to try this one out. This includes a little bit of chemistry that we learned last semester, thinking specifically about how to break this bond right here. So give that a try, figure it out. That says fuming sulfuric acid, by the way. I had almost a little bit of a typo there. Okay, so you can't get off too easy. We got to go to the Diablo sauce. This is an example of a synthesis problem, and synthesis problems for this can be kind of tricky. The reason that they're tricky is because you have to think about doing these reactions in the right order to get the groups to go where you want them to go. And so I'm going to think about all three of these groups and where they're located on this ring to think about how I could have added this group onto there. So I see this nitro here. This nitro is ortho and para to those carbons. So that kind of makes sense. That checks out. That must mean that these guys directed him to this location. I do wonder why they didn't direct him here. If they directed him there, he might have been a little easier. So we'll figure that out as we go. What about this? Cool. So this is here. It's near that. Okay. But it's meta to that group. So I do wonder why these two carbon groups are meta to one another, because you would have thought that the one carbon group would direct the other carbon group ortho or para, which means that one of them needed to maybe been a carbonyl that we reduced. Okay, so it might have had to been a carbonyl that we reduced. Do you think it's the pink group or the blue group that was the one that became the carbonyl that we ended up reducing? It was this one. It was this one. So this one used to be this way. It used to look like this. And we had to reduce it. It could not have been this one because why? We have only one hydrogen here. We've got too many carbon groups going on. We'd have to do a whole lot of funky chemistry. I guess it could be done, but we'll just make it easy on ourselves. Okay. So you can do this in a retrosynthesis type of way or a forward synthesis. I think it's kind of nice to just do forward synthesis, but sometimes I have to work backwards. And so I think that sometimes is really helpful. So working backwards one step, wrong direction in my arrows, huh? All right. Thinking backwards, how did we get to there? Well, I mentioned this is probably the last group that was going to get added, right? And the reason for that is because these would direct him there preferentially. But I did mention that why didn't he go here to the less sterically hindered location? That must have meant that we had a blocking group on this ring. So I actually bet we had a nice little sulfonate group on there blocking the place for that the nitro could go to. So the nitro got added and then we had to remove that group. So right before this, the nitro got added. So I'm kind of thinking in a retrosynthetic way, but I'm not using retrosynthesis arrows. And then I'll fill in my reagents later on. Okay. Sweet. Okay, so I gotta go back another step. So this shows the progression of how we could get that nitro group added there to the right location. What about this? Do we want to add our acyl group or our alkyl group first? Now, I think the best suggestion would be to add the acyl group so that it can direct meta, and then we could reduce. So I think we had recently reduced our molecule from this spot. So I think we had this group looking like this. And it was from this molecule right here that we ended up adding that carbon group. Okay, now we're almost done. I think the only thing we need to do really is just add that acyl group onto there. So actually, I think this is another really good opportunity for you to try to fill in these blanks on your own, and then I'll write in the comments what the answer is going to be. So there's 1, 2, 3, 4, 5, 6. So that's a 6-step reaction. So that's pretty hefty. There might be a couple times where there's 2 reactions that go into one step, but I'll let you try to figure that one out on your own and then check your work with mine afterwards. Okay, sayonara, see you later.